So the video is going to be about how to do limits algebraically. But first, let's see what they look like graphically. So the limit as x goes to c of f of x is equal to L can be graphically represented by we have a function f, let's say something like this. And we care about when x approaches the x value of c. Now the function can either be defined at x equals c, but it doesn't have to be. We could also have it undefined at x equals c, such as having a whole or denominator of x minus c. And if we plot this up, we can see really the y value of that whole, or if it was defined there, the evaluation of c would be equal to L. What that means is as I approach c from either direction, from the right or from the left, we can see that the y values are getting really, really close to L. Now, the limit doesn't care about the value at c. It only cares about the values really, really close to c. So the question is how we do this algebraically. F of x is equal to x squared minus 6x plus 8, all divided by x minus 2. So what I want to do is I want to take the limit of this thing as x approaches 2. So what is the limit as x approaches 2 of x squared minus 6x plus 8, all over x minus 2? So how we do this is we algebraically simplify this expression here. So this is equal to the limit as x approaches 2 of x minus 4 times x minus 2, all over x minus 2. And we can see that they both have that factor of x minus 2, which cancels. So this ends up being the limit as x approaches 2 of the simplified expression, which is x minus 4. Now, the original function is not defined at 2. If you plug in 2, 2 squared minus 6 times 2 plus 8, you're going to get 0 in the numerator. And when you plug in 2 in the bottom, you're going to get 0 in the denominator. So this expression is 0 divided by 0, which is indeterminate. But this function is defined at 2. So if I do plug in 2, you get 2 minus 4, which is equal to its limit, which is negative 2. So we can say, therefore, the limit as x approaches 2 of x squared minus 6x plus 8 all over x minus 2 is equal to negative 2. Negative 2 being the value of the limit. So what I want to do is I want to look at the graph of f of x, which is x squared minus 6x plus 8, and also the graph of f of x, which is equal to x minus 4, and explain why these two functions actually have the exact same limit. So if I graph both of these functions, this function, and if I graph this function, we'll start out with the easier one. This is a linear function, up one, right one, and we can see that the graph of this thing looks like this, which we can see that this function is defined at x equals 2. There's a point there, and at x is equal to 2, y ends up being negative 2 because there's the solution point of 2 comma negative 2 is in that curve. Now for this function, it looks almost identical, except this function will be undefined at 2. So the evaluation of this function and the evaluation of this function will be identical for every single x value, except for the x value of x equals 2. Because here it'll be indeterminate, or if you want to say undefined, and here it'll be equal to negative 2. But remember, the function doesn't care about at the point 2. It cares about really, really close to 2 when we're talking about its limit. So as I'm approaching 2 from this side, or I'm approaching 2 from this side, we can see that we get negative 2. We get close to negative 2. And same thing here. As I approach 2 from the right or 2 from the left, you can see that the y value approaches negative 2 in both cases. That's why these two functions, even though they're not identical, they do share the exact same limit. So we're just going to algebraically simplify and evaluate limits. The limit as x approaches 4 of x squared minus 16, and then we have x squared minus 5x plus 4. So what we want to do is we want to algebraically simplify, this new f of x, and it tends to be done by factoring for the first part, and then we'll show you the other methods as well. So this is the limit as x approaches 4. This is the difference of squares, so it factors into x plus 4 times x minus 4. You can think about multiplying the negative 16, and since there's a 0x here, adding the 0. And for this one, we can factor, I need two things that multiply to positive 4 by adding negative 5. We're going to get an x minus 4, and then we're going to get x minus 1. Now, you can see that they have that common factor of x minus 4. So this ends up being the limit as x approaches 4 of, the simplified expression, which is x plus 4 all over x minus 1. Now, no, I can't plug in 4 in here. If I plug in 4 in the numerator, it'll become 0. If I plug 4 in the denominator, it'll be 0. So we have 0 over 0 again. But I can plug 4 into this expression. This expression doesn't have that hole at x equals 4. So I can just plug it in. This is going to be, plug in 4 into x in both locations. 4 plus 4 all over 4 minus 1. So this is going to be equal to 8 over 3. So that, that's the evaluation of this thing's limit. B. If I want to find the limit as x approaches minus root 5 over x plus root 5, we can see I can't plug in negative root 5 again. You're going to get 0 over 0. Now I'm going to handle this using the factoring method first, and then we're going to use the conjugate method next, because the conjugate method tends to be more powerful with your with terms that involve binomial with radicals. So notice that this is a difference of squares, even though it doesn't look like it. This thing factored into square root of this plus or minus the square root of this, so it'll be the same thing, square root of this plus or minus the square root of this. So this is going to be the limit as x approaches minus root 5 of x plus root 5 times x minus root 5 all over x plus root 5. And then they share that common binomial again of x plus root 5. So this is going to be equal to the limit as x approaches negative root 5 of, the simplified expression. Notice this function is now defined at negative root 5, which means I can just plug it in. So minus root 5 minus another root 5 is going to be minus 2 root 5. That's going to be our limit here. Now I want to do B again using the conjugate method. It tends to be more powerful and more general when solving or evaluating limits that have radicals in the binomial. So we'll just do B again. I want to take the limit as x approaches minus root 5 of x squared minus 5 all over x plus root 5. So what I'm going to do is I'm going to multiply this expression by the conjugate of the denominator. So top and bottom, I have to multiply by 1. So this is going to be x minus root 5, x minus root 5. And the only two things I'm going to multiply or expand out are going to be the denominators. In the numerators, I'm going to leave them alone. So this is going to be the limit as x approaches negative root 5. Numerators are not conjugates, so I will not expand them. Leave them factored. But the denominators are conjugates, so when you do expand them, when you FOIL these things out, this times this, x times x is x squared. Outside is going to be a minus 5 root x. Inside is a plus 5 root x. Root 5 times negative root 5 is minus root 25, which is 5. And the beauty of multiplying conjugates is that your inside and outside will add 0. So those are gone. So this is going to be equal to the limit as x approaches minus root 5 of x squared minus 5, x minus root 5, all over x squared minus 5. And we can see that they now share that quadratic binomial, which we can cancel. So we get the exact same expression that this one's simplified to, which means we can just plug in negative root 5 into here and get exactly the same thing. So minus root 5 minus another root 5 is going to be minus 2 root 5. Now, the third most common method of evaluating limits, they tend to always come down to a method of factoring. But sometimes we have functions that are written not in expanded form. Like C, find the limit as x approaches 0 of x plus 5 squared minus 3 times x plus 4 minus 13 all over x. Now, you can test for yourself. When you plug 0 in the numerator, you get 0. Plug in 0 in the denominator, you get 0. So this is, again, 0 over 0. What I want to do is I want to expand that numerator. I have powers and multiplication and subtraction, so it's not useful to be able to factor that numerator as it sits. It's far too complicated. So I'm going to expand it first. So just order of operations, powers first. So x plus 5 times x plus 5 minus 13 all over x. Now we do all the multiplication, and remember that you have to FOIL or distribute over binomial. So this is going to be the limit as x approaches 0. X squared outside is plus 5x, inside is plus another 5x, last is plus 25. Multiply here this monomial over that binomial, so 3x minus 12 minus 13 all over x. And this is what I mean by an expanded form. It's just term plus term plus term plus term. So it's the expanded form of terms, which really allows us to condense and then eventually factor this. So limit as x approaches 0 of x squared, 5x is 10x minus 3x is going to be 7x. And then 25 minus 12 minus 13 is going to be 0. So this large expression in the numerator just simplifies to this binomial all over x. Now that we have this in simplified form, expanded over expanded, I can see if I can factor and cancel. And you can see that the numerator has a common factor of x. Factor out the x, I'm left with x plus 7 all over x, and those x's will cancel. So this is going to be the limit as x approaches 0 of x plus 7. This function is defined at x equals 0, which I can plug it in. So 0 plus 7 is equal to 7. And that's the limit.